Hey guys, we're back. We got the fourth installment of the solutions chapter here. This is 11.4. It's called Colligative Properties. You probably have never heard of these, and they're kind of cool. You guys really appreciate colligative properties when you are when it might be a snow day or something like that, or it's what keeps you away from getting a snow day. That's why they put salt on the roads. That's why we put antifreeze in our cars and things like that. So that's what we're going to be doing today. There is some math involved. There's some concepts and math involved as well. So let's get started, Mr. Wing. You ready?
I'm excited.
He looks so excited. All right, here we go. So this is vapor pressure. You want to talk about, Mr. Wing?
You got this one.
All right, man, you got it. So essentially, imagine we poured a cup of water into here, and we have some water in the cup. And if we put it in there, you've basically spilled water on the table before, and you know that when you come back a day later, it's gone because some of the water evaporates. Okay, now as soon as we pour the water in here, it's going to evaporate. It's not all of it, just some of it's going to evaporate up here. What's that?
Just the one, like the molecules on the surface.
Yeah, the molecules on the surface are going to evaporate. They're going to leave the liquid surface and come up here and be in the vapor phase. And then over time, they'll condense back into here, and then they'll just keep going back and forth, and keep doing that. They'll reach something called equilibrium. So, but the thing is, there will always be vapor above this liquid. And that vapor is going to put pressure on these outside of this cup and the top of the cup. We learned about pressure last unit. So that's what's causing these molecules are going to hit the sides of the cup. They're going to create a lot of pressure, and that's why it's called vapor pressure. All right, so we're going to see what happens to vapor pressure when we dissolve salt or sugar inside here and see what happens. All right, does that make sense, Mr. Wing?
Yeah, that makes great sense to me.
Well, I'm glad it does. All right, how about this one? This is the old phase diagram, brother. What do you think of this?
I love this picture. It really brings joy to my heart. So let's look at the original phase diagram. So if you can scroll over that, yeah. We learned about this. We learned that based on temperature and pressure, substances would be a solid, liquid, or a gas. And you guys did a great job with that in the last unit. But what we want to look at is what happens when we add a solute to a solution, and when we add so much, how is it going to change the points where things are going from a solid to a liquid or a gas to a liquid. And so if you look at the light blue lines, you can see that our Y shape is kind of shifted to the left and down. And that's what the colligative properties are doing. It lowers the vapor pressure, and it will change our freezing point, and that's called freezing point depression. And that's one of those things where you're going to see temperature on the bottom, the x-axis. As we go to the left, we're getting colder. So if you look at something that's in the solid phase, it's smaller with colligative properties than it was with originally if it just was a pure substance.
Right. So I never really put out the definition of what a colligative property is. So just to listen to what the colligative property is, it's any property that is only affected by concentration. That's why we put it in this chapter here. It doesn't matter what the stuff is, kind of, but it just matters what the concentration is. So 3 molar sugar would have the same effect as 3 molar ethanol, something like that. So as long as it's 3 molar, it's going to have the same effect. But right here we are at normal pressure, Mr. Wing, right?
Yes.
So if this is normal pressure and we go across, we would raise the temperature up, right? And then if we got to the black line, like it was pure water, this would be 0 degrees Celsius right here, right?
Yeah.
That's where it would go from ice to water and it would melt. And then right here, what temperature would that be if that was water?
100.
100. So that's basically the freezing point and the boiling point of water. But when we add salt to it or sugar or something to water, it lowers that vapor pressure, right? So that vapor pressure is now lowered, and now we're on that light blue line. Now, Mr. Wing, look at this. As we start really, really low, like negative 30 degrees Celsius, and we start heating it up, look at that. It's already going to start melting here way below 0, like negative 10 or something, right? And then we go through. So it's literally lowered that freezing point, which is what you call freezing point depression, right? And
And
then
this
what
is
happens
where,
over here on the boiling point, homie?
and then we expand in the opposite way.
Mhm.
We're boiling point happy.
Happy. We've elevated. I get it. I get the difference between depression and happy. I got it. It's a good one. So here we are normally at 100. Now the boiling point is now like 110 or something like that. So we definitely increased our boiling point and we've decreased our freezing point, right?
Yes. Just real quick examples. Boiling point elevation. Why would we want to boil something at a higher temperature? I've heard about like chefs, and if they're boiling a bunch of pasta and they're trying to get it done quicker, maybe they will try and boil it at a higher temperature. So they want to add salt to water, so that way it boils at a higher temperature to cook the pasta faster when they're trying to dish it out as quickly as possible in a lot of catering events. And then for freezing point depression, this Mr. Word kind of talked about the putting salt on the roads before a storm to try to lower the freezing point of water, so that way there's less ice on the road.
Right. So if we have like, let's say it's going to be -5 degrees Celsius, which is like, I don't know, what, 27, 26 degrees Fahrenheit, that would normally freeze on the road. But actually, if we put salt down, it's still going to be in that liquid phase. And I think we should show them the next slide that shows how the liquid and solids work. Okay. So here we are as a solid. Let's say it's -30 here. We raise the temperature and then we saw that heating curve where it would be flat for a while. And that's at 0 degrees Celsius. We would actually be melting our ice at 0 degrees Celsius. And then we raise the temperature again once all the ice is melted. And then we would be flat again. And that's where we're starting to boil it. And then once we boil, the temperature would go up again. But anyway, the freezing point of water, of pure water, is 0 degrees Celsius. And the boiling point of pure water is 100 degrees Celsius, right? So then if we actually add salt to this water, here's what really happens now. We've lowered that freezing point, which is
Depression.
Good. And then we have raised that boiling point. So what phase of matter is what phase of matter did we extend, Mr. Wing?
The liquid phase.
That's right. So that's kind of important to see. I always like to use the example of antifreeze in your radiator of your car. You want to put antifreeze and water in there. You don't want to put just antifreeze or just water in your radiator because what we can do is if we put a lot of antifreeze and water in there at a right mixture, it can extend this liquid phase. And we don't want the water to get so hot that it gets the steam because it will expand in the hoses and break your hoses of your car. And we don't want it to freeze in the wintertime because ice takes up more volume than water. So it'll break your pipes again. So we're trying to keep everything in the liquid phase as much as
Hence antifreeze.
Antifreeze. They don't call it anti-boil. Wonder why they don't call it anti-boil. Who knows? All right, I think we're gonna have to go through some problems with it, Mr. Wing.
Let's do some math.
All right, yay! First, you learn these formulas here. Go ahead and go through these, Mr. Wing.
Okay, so there's lots of weird symbols, and it may look scary to you, but I promise it's not. These problems are not any harder than anything we've done. So, who remembers what that triangle is before the T?
I do.
Oh, what is it?
That means delta, which means change.
Okay, so the whole point of this is we're looking at what's the change in boiling point for the first formula. Notice the little b subscript, that means boiling, and look on the right, we have the subscript F, that is freezing. So these are the exact same formulas except for you got to know if you're looking at something's boiling point or freezing point.
Can you believe this? I mean, delta TF, dude.
Totally.
Right.
And then we got this I. This is a Van't Hoff factor. And we're going to talk about this in the next slide. But basically, it's going to be a number pretty much between 2 to 5 most of the time. And then
Could be a 1.
Or 1. That's true. KB is a boiling point constant. You'll always be given this. So it's just like Avogadro's number was 6.02 times 10 to the 23rd. There's boiling point constants and freezing point constants, so that'll always be given. And then lastly is M. We have molarity.
Molarity?
And that is for the boiling point. Or, sorry, molality. Sorry, lowercase m. I can't read. So molality, this is why we had to learn about molality earlier in this last section, because we're actually going to use it and apply it in these formulas.
That's right. So we don't use molarity here. We use molality. One other thing I wanted to point out, Mr. Wing, is that these Ks are always the same. This KF will always be the same, but only for that one substance. So water will have a different KF than ethanol, and it'll also have a different KB than ethanol, which would be different for any solvent. It's always specific to the solvent. It doesn't. So this K can change depending on what your solvent is, but it'll always be the same for that solvent, right?
Yep.
All right, you ready to move on?
Yes.
Okay, let's go through this. Let's see what we got. All right, so this is the first problem we're going to do. Notice I just wrote it up here as delta T equals IKM. Wait, we didn't go through this slide.
Yeah.
This is important, Mr. Wing.
I was gonna say, wait, I thought we had to talk about the I value.
I know, they were like, wait, I don't know what the I value. All right, you want to go through this one? Looks
Yeah.
like we got the words broken off there. We didn't mess with that. Our pictures are going to mess with that over there.
Well, I'll just read it.
Okay.
The Van't Hoff factor, this is our I in the formula. When salts dissociate in solution, they break apart into ions, hence the I. Colligative properties are dependent on the molality of total particles in solution. Okay, so what does this actually mean? When we look at salts, we learned that salts dissociate when they're mixed with water. So if you look at this first example of sodium and chlorine, the sodium and the chlorine are going to break apart. They're going to become single ions. They're going to be surrounded by water. So when sodium chloride breaks apart, there are two particles. There's a sodium ion and a chlorine ion. So that is 2. So the Van't Hoff factor, the I, will be 2 if you're using sodium chloride.
Hey, Mr. Wing, can you tell me what kind of intermolecular force is in between these two?
Looks like an ion dipole.
Woo-hoo-hoo! Man, blast from the past, huh?
Oh, yeah.
Beautiful. So sodium chloride has 2 particles in it, right?
Yes.
So are you telling me that its Van't Hoff factor would be 2?
I am.
Attaboy.
Yes, sir.
I like it. All right.
And so calcium chloride has 3 particles because when it dissociates in water, you're going to have 1 calcium and you're going to have 2 chlorines. 1 plus 2 is 3. So similar to aluminum sulfate, we have 2 aluminums, you have 3 sulfates, so there's going to be 5. So their Van't Hoff factor would be 5 for aluminum sulfate. You just got to think about how many ions these are going to dissociate into.
Right. I want to make sure that they don't try to dissociate this sulfate. Sulfate is a polyatomic ion. You're not going to break it apart into sulfur and 4 oxygens. Make sure you know what your ions are. Aluminum sulfate. So you got 2 aluminums and 3 sulfates, 5 particles. Right.
And then the last thing is molecules that do not dissociate are things like sulfur dioxide,
methanol,
and sugar, or glucose, sorry. These are molecules, and we learned the difference between ionic compounds and covalent molecules. These are all of our molecules. So what if these don't dissociate, Mr. Worth, what should we put for the Van't Hoff factor if I have a situation where I'm looking at sulfur dioxide?
Well, it's not going to dissociate, so it's going to be 1 particle in solution. So that's just going to have a Van't Hoff factor of 1.
Oh,
so
okay.
Each one of these will have a Van't Hoff factor of 1. Anytime you see a molecule, it's just 1.
Perfect.
All right, ready? Now we're ready to go through those
together.
Okay, so here we go. So I got the delta T equals IKM. This can be either a B or this could be an F. It doesn't matter. It just depends on what we're looking at. Now, what I'm going to do is I'm going to do 2 problems in one because it's special night, and we're going to see how we do. It says, what would be the boiling point and freezing point of a solution that contains 0.80 moles of calcium chloride dissolved in 200 grams of water? Okay. Sometimes I'll say something like, what would be the boiling point? I can't remember what else I was going to say. But there's things that you can say that are different like that. Instead of, I might instead say it's dissolved in 200 grams of water. I'll say it's an aqueous solution. So that way you know it's dissolved in water, just so you know. But let's look and see what we got. So what it's asking for is what is the boiling point and freezing point? So if it's asking for the new boiling point, the new freezing point, we have to find out what the change is first, all right? So we're going to do the I first. Let's see what the I is. And it's calcium chloride is the solute being dissolved. And Mr. Wing just went through that with you on the last one, right? And it's going to have 3 ions. It's going to have 1 calcium 2+ and 2 chloride ions right there. The next thing we got, of course, is our K. So let's do the boiling point one first. So the K we would use would be this 0.51 right there. And then the molality is what we need to find. Now, the molality solution, remember, is moles of solute per kilogram of solvent right there. So if we look at that, the molality is going to be 0.80 moles of calcium chloride divided by 0.200 kilograms. I just moved the decimal point over 3 to the left, or divided by 1,000. So we got a molality of 4 molal. Does that sound good, Mr. Wing?
That sounds perfect.
You ready to plug and chug?
Yes.
All right, so we got the I, 3. We can now have the KB, which is right here. And now we have the little M, which is right here. We just plug all those in, and we get this right here, and we end up getting 6. Now that's our change in our boiling point.
That's not the final answer?
That's not the final answer, sir. That's how much the boiling point is going to go up.
Oh.
So we have that. Now the original boiling point of water, which is, some people forget what it is, it's 100 degrees Celsius. And then we've just now raised it up by 6 degrees Celsius, which now means the new boiling point of water is 106 degrees Celsius. Sound good?
Hey, Mr. Worth, how do you know that that you added 6 degrees? Why didn't you subtract 6 degrees?
Because I remembered its boiling point elevation based off that lowering of the vapor pressure, right?
Or boiling point happy.
Boiling point happy. Now let's go through the freezing point one. It's the exact same formula. The molality is going to stay the same, but we're going to have a new K value, all right? And that new K value, of course, is here. It's negative 1.86 this time. So we have that. So that means it's going to drop it 1.86 degrees times these two things right here.
Sounds depressing.
It is very depressing. So it's negative 22 degrees Celsius is how much we're going to lower the freezing point. And since the original freezing point of water is 0 degrees Celsius, our new freezing point is negative 22 degrees Celsius. So imagine if it started snowing and it was at negative 10 degrees Celsius. Well, if it was pure snow, it would actually be frozen. But when that lands on salt, that's going to actually say, no, you're not going to freeze at negative 10 degrees Celsius, because you won't freeze until you get down to negative 22. So it'll stay as a liquid, right?
Speaking of which, if I worked for the state of Ohio, ODOT, would I want to use sodium chloride or calcium chloride to put down on the roads? Which one is going to lower the freezing point more?
It's going to be calcium chloride is going to lower it more because it's got 3 ions versus sodium chloride, which only has 2 ions, right?
Yeah.
But as a politician, I would use sodium chloride because it's much cheaper. And they actually use on the roads magnesium chloride. And my wife always talks about it because she's one of the, used to be the chemist that developed the paint that went underneath the car. And the magnesium chloride that they spray down the road is really corrosive to a car engine or car metal parts on the underside. So, so always wash your car in the winter more than you do the summer, right?
That's a great piece of advice.
Well, it's what I'm here for, brother. All right, you ready?
I think we're done, right?
No, I think we got one more slide.
Oh,
Just one more. I'm pretty sure. And let's see if we can figure it out. There it is, right there. You're gonna have to read this to him because I have it in the way again.
okay. Solution A is an aqueous solution that contains 2 moles of magnesium chloride dissolved in 600 milliliters of water. Solution B is an aqueous solution that contains 3 moles of sodium chloride dissolved in 500 milliliters of water. Which will have a lower freezing point?
Now, the reason why I put this slide on here is because I saw this on the practice test and the test, so they need to kind of know how to do this. The cool thing is we use the same exact formula or whatever. It could be delta TB, delta TF. It doesn't matter. I've got a B and an F here. That's kind of weird, but you don't want to worry about this right here. But the cool thing is that both of these solutions are aqueous, Mr. Wing, right?
Yes.
These are dissolved. They're both dissolved in water, which means if the KF is based off of water, they're both going to have the same KF. So let's just ignore that, right?
We just get rid of it. Don't even need to do it.
So what we're going to do is I know that this I times this M, whichever one is bigger, is going to give us our bigger change in boiling point or freezing point. So if this was delta TF, which is what it should be, I mean delta TF. So if we have that right there, the bigger the number of these are, the bigger it's going to lower that freezing point. The more it's going to lower that freezing point. So let's go through them real quick. You ready?
So
here's solution A. All right. Notice it has 3 ions. Why has it got 3 ions, Mr. Wing?
Because that's magnesium chloride. Magnesium has a +2 charge, so there needs to be 2 chlorines to balance out that magnesium.
Yeah. So we got MgCl2, which is going to give us 3 ions. Here's its molality, 2 moles in 0.6 liters. And if we take 3 times 2 divided by 0.6, you end up getting 10, right? And solution B, of course, has 3 moles of sodium chloride. Now, sodium chloride has 2 ions in it, right?
Yep.
And let's see, and then look at its molality, 3 moles divided by 0.5. So if we multiply all those, we get 12, right? So this being the bigger number means it's going to have this right here, it's going to have a bigger change in my freezing point, which means it's going to lower it more, right?
And I just want to point one more thing out, Mr. Worth. You see that we divided by 0.6 liters, and molality is supposed to be kilograms, but because this is water, we know that water has a density of 1 gram per milliliter. So it's milliliters or liters and grams are the same thing. So that's why this was okay, because it was pure water.
Good call, brother. Good call. Yeah, like a 1 liter is equal to 1 kilogram. So 0.600 liters is the same as 0.600 kilograms. Good call. Glad you caught that. All right.
All right.
We're done, right? Look at
Yes.
this. Get this joke? It's hilarious. All right. Mr. Wing, you have a good rest of your day, sir.
You
I'll
too.
see you tomorrow. All right.
Goodbye.
Yeah.